All right, thank you so much for joining us today. Now, the question that comes in mind is what if the differential equation is not separable? For example, this differential equation that we have here is not separable. So, do we just leave it like that or we have a new way of solving it? Yes, we have a new way of solving it. Now, from here, whenever we see that the differential equation is not separable, the next thing that we need to think about is we need to think about homogeneous differential equation, because the function here is in a way that we cannot separate the x from the y. It means that we need to use the idea of, or we need to think about homogeneous differential equation. So now let's talk about homogeneous differential equation. Now it's very simple with homogeneous differential equation. The idea is that we have a function and we are saying that this function is homogeneous if we can multiply x by, let's say, a scalar and multiply y by a scalar, or let's say a real number, such that when I'm done multiplying it by a scalar, we can factor the scalar out, which will come with what? A degree, and then I will have my function back. So my function was h of x, y. And when I multiply x and y by lambda, I'll be able to bring lambda out and get my function back. So you see, I multiply this one by lambda and I was able to bring it back. So that is the idea. Now this n here is the degree of the homogeneity, and then the lambda is any positive real number with n not equal to 0. Now let's take some example and then let's see how we can do this. Now, before we learn how to use the method, well, let's test and see if some functions are homogeneous or they are not homogeneous. For example, let's look at this. Now, as we said, what we just need to do is first, since we have h of x, one thing that we need to know is with this one here, we assume that if we are using h of x is the same as dy over the x. So let's have that one in mind. So this is the same as h of lambda x, lambda y, which is equal to lambda x cube. So we don't just do it like this, lambda x cube. No, we put it in parentheses and then we make sure all of them are there, plus 2 lambda x all squared. Then I have y2, so I need to multiply the y2 by lambda. Then plus 3 lambda x lambda y all squared plus 4 lambda y to the power 3. Good. Now, what am I going to get? This is the same as lambda to the power 3 x to the power 3 plus 2 lambda squared x squared times lambda y plus 3 lambda x times lambda squared y squared plus 4 lambda cube y cube. So see what is happening here. Now this is the same as lambda cube x cube plus 2. I have lambda here, I have lambda here. So this is going to give us lambda cube x squared y plus another lambda cube x y squared plus 4 lambda cube y cube. So the magic that we can see from here is I have lambda cube throughout. So I will be able to factor the lambda out, and then I'll be left with x cubed plus 2x squared y plus 3xy squared plus 4y cubed. Good. So I was able to factor the lambda out. Now, what is this function in this parenthesis? This function in this parenthesis here is this, which is the same as h of xy. So I can write this one as lambda to the power 3 h of x y. So I was able to multiply 2 by lambda, but I was able to bring the lambda out and then the function stand on itself. So this is homogeneous. The function here is a homogeneous function and it has a degree of 3. So degree is equal to 3. So the function is homogeneous and it has a degree of 3. So basically that's how we do it. Let's pick another function and let's try from other perspectives too and see. Gen of x lambda x lambda y is equal to, so same thing, I multiply x by lambda plus I multiply y by lambda divided by lambda x minus lambda y. Now what are we going to get? This is the same as, I can factor lambda up out on the top, and then down to I can factor lambda out. Now this we can cancel it, but because we are talking about how to get a degree, then what I can do is I can use indices and write lambda over lambda as lambda 1 minus 1, because this is to the power 1, this is also to the power 1. So indices, that's what you're going to have. And this one will be x plus y divided by x minus y. And guess what I'm going to get? We are going to have something like this, lambda to the power 0. And what this function? The function x plus y divided by x minus y is this, which is gen of x. So I was able to get my gen of x, y out. And here the degree here is equal to 0. So the function is homogeneous and the degree is 0. We have some functions that are not homogeneous. For example, I can even modify this function and write it as xy plus y over x minus y. This is not homogeneous because this is going to give us lambda squared, and this is going to give us just lambda to the power 1. And when I factor it out, so I'm going to have lambda inside. So for example, this is what I mean. This is going to be lambda x, lambda y plus lambda y divided by lambda x minus lambda y. This is going to give us lambda squared xy plus lambda y divided by lambda out x minus y. Now when I factor lambda out on the top, I'm going to still have lambda xy plus y divided by lambda x minus y. So you see that we factor lambda out, but the function is still having lambda. So this one, we cannot call this one h of gen of xy as we did for this one. So it means that since the function depends on lambda, then this function is not homogeneous. So always when you are doing it, try and check the degree. Add the degrees together. This is having a degree of 1. When you add it, you get 2. And since this is 1, then the function is not homogeneous. Another function that we can talk about is the sine function. If I have a sine function, which is, let's say, this plus cos y, and this is h of xy, we can see that when I plug in lambda here, I cannot put the lambda back. So there is no way the function is going to be homogeneous. We can talk about exponential function. We can talk about the length function. All these functions are not homogeneous because when you put the lambda inside, it becomes an angle and you cannot pull it back. So basically that is how we can determine if a function is homogeneous or not. Now we need to learn how to solve a differential equation using the homogeneous differential equation. But there is a rule to it. The rule is, we saw that this one we're able to get a homogeneous, but the degree is what? 3. But a function can be homogeneous, but if the degree is not 0, then we cannot use the method for solving differential equation. So that's another thing that you need to know. Now this one has a degree of 0. So this equation here, or this differential equation here, we can use the idea of what? Homogeneous method to solve. So that is what it was saying from here. For us to use the homogeneous method, then if I have a function f of x, y, and I plug in the lambda by x, lambda by y, then after doing everything, the function should be lambda to the power 0, f of x, y, before I can use the method to do it. So these are the method. First, we are going to use the idea of U substitution. Or let me say we are going to use substitution, where we are going to say that let Vn equals y over x, and this will imply that y is the same as Vn of x. And one thing that we need to know from here is that Vn is not constant. Vn is not constant. It's a function that we can differentiate, not just a constant function. So that's one thing that we need to also learn from here. So after we've gotten this function here, what we are going to do is we are going to differentiate the function. We are going to differentiate this function and equate it to this function. Or let's say we substitute it into this function. We're going to have something like this. We will do it for you to understand it. So don't worry. And then when we are done, we just integrate it and then we just do back substitution. But all the methods that we are learning, one thing that we need to learn from here is that homogeneous, it get to a place that the function now becomes separable. So we should be able to take the previous video, for example, very carefully, because we need to understand it, because all the method it comes back to separable. So after we've done the substitution, you will see that when you simplify it, now the function will come back to what is separable, and we need to use the separable method to solve, and then we just go through the process. So let's take example and then let's talk about how we can solve how we can solve homogeneous differential equation. So we want to solve this and then given initial condition. Another question that you need to ask yourself is, you see this question is open. We know that we are working this under homogeneous differential equation. So we see that definitely we need to use the method. But I'll show you the tricks how to identify if, let's say, you are writing a quiz, a midterm, or an exam, and the function is open like this, and you don't know which method to use. So we will learn all these tricks as we are going through these videos. So now let's start. We know that for us to start a homogeneous differential equation, the standard function should be like this. It should be like this. Something like h of xy is equal to this. And as I said, something like this is kind of dy over what? Dx. So it's like we need to have dy over dx equals to something, and the coefficient is 1. So looking at the example, we don't have the coefficient to be 1, so we need to clear the coefficient. So let's start. X squared dy over dx is equal to y squared minus xy plus x squared. So since we want the coefficient of this to be 1, we divide through by x squared, and we are going to have dy over dx, which is equal to y squared minus xy plus x squared divided by x squared. Good. Now let's assume that we don't know that this is open. We don't know that this is homogeneous, and we need to check if it's homogeneous. So as I said, anytime you see a differential equation question and you are solving, the first thing that you need to think about is you think if the function is linear differential equation, right? So let's check if this is linear. This is not linear, of course, because linear we should have it in the form of dy over dx plus gen of x, y is equal to gen h of x, and there is no way we can write this in this form. Look at the way it is. You see that there is no way we can write it in this form. Good. So it means that linear differential equation is out. The next thing that I need to think about is separable. Let's see if we can do separable here. Now here we cannot separate the y alone from the x, because this is y squared, and I have just y here, not y squared, it's just y. So it's not going to work. So separable is not going to work for this. Now let's think about homogeneous. Is it homogeneous? Yes, it's homogeneous because we have the degree here to be squared. This one 2 is squared. This one 2 is squared. This is 1. This is 1. When I add it, I get a squared. So whenever you are using homogeneous, that's one trick that you need to know. All the degrees should be the same. If they are not the same, you should be able to add them and get to be the same. So this is homogeneous, but let's solve it. So as I said, here our dy over dx is just a function of x and y. So let's assume that this is f of xy, which is equal to y squared minus xy plus x squared divided by x squared. So we want to check if it is homogeneous, then we start trying the idea of solving, right? So let me just do it here. So now let's put in lambda. So lambda x, lambda y, and this is going to give us lambda y squared minus lambda x, lambda y plus lambda x all squared divided by lambda all squared. This is like this. This is going to give us something like lambda squared y squared minus minus lambda squared xy plus lambda squared x squared divided by lambda squared x squared. So you see that this one becomes homogeneous because now we see that all the lambdas is having the same degree. That's the reason why we need to check the degree very well. So x squared, y squared minus xy plus x squared divided by lambda x squared. Then since I have lambda here, since I want a degree, I'll write it as lambda x squared minus 2, and then this is y squared minus xy plus x squared divided by x squared. Now we see that this one in the parentheses here is the same as this, which is the same as f of xy. So we were able to multiply through by lambda, and we're able to get the function back. And the degree is 0. So it means that now we can conclude that this function here is homogeneous and it has a degree of what? 0. But learn one thing here. One thing that you need to learn is, you need to be very good in the situation that you can use eye test to see that, oh, good, this function is homogeneous and it's having a degree of 0. So that if the question is open like this and it's not asking us to check whether it is homogeneous and state its degree, we can just do it straight without going through the whole process, because it's kind of like time wasting for doing this for no mark. So we just need to go through the process. So the first thing that you need to do is, after I have gotten here, I see that this is the degree 2, this is also having a degree 2 divided by a degree 2. It means that the degree 2 will cancel the degree 2, which is going to give us 0. Like it will be going to be 2 minus 2. If this one is 3, 3, 3, and this one is 3, there's going to be 3 minus 3, which is going to be 0. So you will use that strategy to identify it, and then from there, you will see that, okay, the function will be homogeneous. So let me use the homogeneous method to solve. So let me end it here with homogeneous, and now let's go back to solving it. So our function was dy over dx is equal to y squared minus xy plus x squared divided by x squared. So now we want to go through the process of solving this. So now we know that it's homogeneous and the degree is 0. So what we need to do is we need to let our substitution then to be equal to y divided by x. We are saying that this implies that y is equal to then x. So with homogeneous, just remember this substitution here. Then is equal to y over x. And when I make y the subject, I get something like that. Now, as soon as I get y to be this, what I need to learn now is, now I need to know that this is dy over dx. So I need to differentiate this with respect to x. So let's do that. Now dy over dx is equal to, now we are using the idea of product rule. As I said, then is not constant. So when I maintain then I differentiate x, I'm going to get 1 plus, now when I maintain x, then I differentiate then with respect to x. So this is what I'm going to get. And when I simplify it, I'm going to have dy over dx, which is equal to then plus x then over dx. So you see what we've done. So let me call this one equation 1, and let me call this one equation 2. So we see that equation 1 and equation 2 are the same, because this is dy over dx, dy over dx. So I can equate the right to the right here. Okay, let's do that. So we know that equation 1 is the same as equation 2. So we have then plus x then over dx, which will be the same as y squared minus xy plus x squared divided by x squared. So as we learned from here, this is the one and this is the one. So we have equated them. But we are moving, as I said, after we've done with the substitution, we need to move back to separable differential equation. But the only problem here is we have then, we have x, and we have y. We need to have two variables so that we can go with separable. But we know that by making then is equal to y over x, we saw that y should be the same as then x. So we need to change y to Vn x, but y is equal to Vn x. So I'm going to do substitution for that. So I'm going to have Vn plus x divided over the x, which is the same as Vn x squared, right, minus x times Vn x plus x squared divided by x squared. So I'm going to have Vn plus x divided over the x is equal to Vn squared x squared minus x squared Vn plus x squared divided by x squared. So I'm just simplifying this. Now Vn squared plus x, Vn plus x divided over the x is the same as, here I can factor x squared out. So Vn squared minus Vn plus 1 divided by x squared. Then the magic will happen. This will cancel this. Then I'm going to have Vn plus x divided over the x, which is the same as Vn squared minus Vn plus 1. Good. So now we have two variables, which is x and Vn. So now we can think about separable method, like way of solving separable. So we need to group Vn to Vn, Vn to the Vn, and then the x to x. So Vn squared minus Vn plus 1 minus Vn again. So I just move this guy to the right, and I'm going to have x the Vn over the x, which is the same as, this is the same as Vn squared minus 2 Vn plus 1. And what am I going to do? I'm going to try to basically group like terms. Vn function with the Vn, and then x function with the x. So the first step is multiply through by the x, and we're getting something like this. But this is not good. Why? Because this is Vn function with the x, and then x function with the Vn. So we need to interchange it, right? So how can we do that? We can do this by dividing this one by x and dividing this one by x. So it means that here is going to be 1 over x here. So I'm going to have it to be 1 divided by Vn squared minus 2 Vn plus 1 the Vn, which is the same as 1 over x dx. So I divide through by Vn squared plus 2 Vn, no, minus 2 Vn plus 1, which is going to be this. And then divide through by x, which is also going to be this. So basically, you want to bring this one here, and you want to bring the x here, so it becomes inverse. Now, since it's separable, we're able to group them. We need to just integrate. So I'm going to integrate 1 over this. But you see, integration, as I said, you always need to be passing a way that you will be okay. So what can I do here? I can simplify this quadratic function here as Vn minus 1 squared. How did I do that? When I expand this, I'll get this function here. So that's basically the idea. Then I'll integrate 1 over x dx. Now this can be written as Vn minus 1 minus 2 the Vn, because this is 1 over that. So when I want to take the 1 over, become minus. Then we know that when we differentiate ln x, we get 1 over x. So when I integrate 1 over x, I get ln x plus, let's say, c1. So what is left is the left hand side for us to, integrate. Let's use substitution. Let u to be equal to Vn minus 1. It means that the u is the same as the Vn, right? So I differentiate this. Okay, so let me just do it. So the Vn over the u over the Vn is equal to 1, and this implies that the u is the same as the Vn, right? So now let's go up here and just continue from there. Let me move this guy to this side. So now we are going to have integration u to the power minus 2 du, right? Because now we know that Vn minus 1 is u. So I'm going to have u to the power minus 2, and then Vn, the Vn here is the same as du. So I'm going to have something like this. Then this is the same as natural log of x plus c1. Now let's do integration for this. and I'm going to have u minus 2 plus 1 divided by minus 2 plus 1 plus, let's say, c2, which is equal to the natural log of x plus c1. So what am I going to get from this? This is the same as minus u minus 1 plus c2, or let me just move it, natural log of x plus c1 minus c2. So this is going to give us 1 divided by u by minus here is equal to natural log of x plus c. c1 minus c2 is still constant. But what is u? We know that u is vn minus 1. So let's do that. U is vn minus 1. So this is going to be 1 divided by vn minus 1, which is equal to this. But whenever we have our general solution, we have it in terms of x and y. So it means that we need to take out the vn. What was vn? Vn is equal to y over x. So we are going to have this one to be minus 1 divided by y over x minus 1, which is equal to the natural log of x plus c. So let's do some small manipulations here. So this is the same as minus 1 divided by x divided by y minus x, right? So this is divided by 1. So if this one is divided by 1, if we are using my trick, y divided by x minus 1, this is divided by 1. So this will multiply this, which is going to give us y, and then this will multiply this, which is going to give us 6x, all divided by this will multiply this. So we go this first, this second, and this third, and we are getting what is there. Then this is going to be ln of x plus c, and this is going to give us minus x divided by y minus x, because of the 1 here is going to reciprocate itself. And this is what we are going to get. This is our general solution. Good. So this is general solution. This is our general solution. But I think they've given us initial condition, so it will help us to get the particular solution. So we know that y of 1 is equal to 2. This implies that y is 2 and x is equal to 1. So let's see what we can get. Minus 1 divided by 2 minus 1 is equal to the natural log of 1 plus c. What are we going to get? So minus 1 over 1 is equal to natural log of 1 is 0 plus c, and c is equal to minus 1. So it means that we can now write the particular solution. So I'm going to have minus x divided by y minus x is equal to the natural log of x minus 1. And this is the particular solution. So you see what we did? We moved from homogeneous to separable, and then we finish it up. So it means that you will see that all the method will come back to separable. So please make sure that you are very good with separable method. Let's take another example. Let's take another example to practice. So this one, there is no initial condition, so we just need to find the general solution. So let's go. The same thing, dy over dx, x y minus x squared is equal to y squared. So we need to make sure that the coefficient of this guy is 1. So we are going to have dy over dx, which is equal to y squared divided by xy minus x squared. But the question is this homogeneous? Yes. Why? Because the degree here is 2, the degree here too is 2, and the degree here is 2, because x is having 1 degree, y is having 1 degree. When you add it, you get 2. So you have 2, 2, 2. So it's going to be 2 minus 2, which is going to be 0. So this is homogeneous, and the degree 2 is 0, because the down is 2 and then the top is 2. So basically, we can go away with the idea of checking whether it is homogeneous or not, right? And then just start. So since now we see that it's homogeneous, what we just need to do is now we need to use the Venn substitution, right? So Venn substitution, we let Venn to be equal to y over x. So practice will make you remember the procedures. and then y. This implies that y is equal to Vn x, and you see that everything that we are doing here, this step is constant. Like for example, this one, you see this step right here, this one is always constant, the same thing that you are going to get anytime you are dealing with homogeneous. This step that I've circled here is the same thing. So you see that it's the same thing that I'm doing here. I'm letting Vn to be equal to this, then y will be this, then I will differentiate it again. So dy over dx will be equal to Vn, I differentiate x, plus I maintain x, I differentiate Vn. And this is dy over dx, which is equal to Vn plus x dVn over dx. So you see that the step here is the same as the step that we did from the other one. When you are doing need to, if I give you a trial question, you are doing it. So I'm showing you the tricks. When you get this one, the same process. So you should just even know this one, the procedure. When you learn it, that's all. And then the procedure goes the same. It's just the integration that changes. So when I get this one, I name this one equation 1, the same thing, and this equation 2. So the next thing to do is equate equation 2 and equation 1. That's all. So equation 2 is the same as equation 1. So I'm going to have Vn is the same as Vn plus x dVn divided by dx is equal to, then my new function, which is y squared divided by xy minus x squared, right? And the same process again. After I have equated them, I need to remember to change my y, right? So I know that y is equal to Vn x from here. So we are going through the same process again, and then we have it this form. And now y is equal to Vn x, so we are going to have Vn plus x dVn over dx, which is equal to Vn x all squared divided by x Vn x plus x squared. And what are we going to get? We are going to have something like this. Let me just shift this guy down small and bring this guy here. Good. So what are we going to get? Vn plus x dVn divided by dx, which is equal to Vn x squared divided by Vn x squared plus x squared. Do you get it? Yes. And we see that this implies that Vn plus x dVn divided by dx is the same as, here I can factor x squared out and I'll have x squared out Vn plus 1. So when I factor x squared out here, I'll have this one. And then the magic happens. So anytime you are dealing with homogeneous, you should be able to cancel. If the degree is 2, you should be able to cancel x squared out. If the degree is 1, you should be able to, the degree is 1 here, from here. You should be able to cancel x out. If the degree here is 3, you should be able to cancel x cubed out. So basically that is the idea. So what are we going to get after the simplification? We are going to have Vn plus x dVn divided by dx, which is the same as, what we left is Vn divided by 1 plus Vn, or Vn plus 1. So the same idea holds again. What we just need to do is we group items. So we move Vn to the left. So you see that the same process again. It's just the function which is different. So minus Vn. So I just move this one to the right. So x dVn divided by dx is equal to, let's find the LCM. Remember, this is divided by 1. So when we are using my trick, we multiply this to this first, followed by this to this, and then we multiply the down. So don't forget this shape whenever you are doing a fraction. This first, so this is first, this is second, and this is third. So how are you going to get this? So first is this times this, as the line shows you. So 1 times Vn is Vn minus, so there is minus here. Then I go second is this. So this times that is going to give us Vn plus 1 divided by third. Third is this times that, and this is going to give us Vn plus 1. It helps you to do fraction very fast. So x dVn divided by dx is equal to Vn minus Vn squared minus 1 divided by Vn plus 1. So now what we just need to do now is we need to make sure that we group items, right? We group items like x with the x and y with the Vn with the Vn. So x the Vn is equal to, the top can be written as minus out. I bring minus out, so Vn squared, right, minus Vn plus 1 divided by Vn plus 1 dx. I hope you got what I done here. When I factor minus out, this is minus, so it become positive. This is positive, so it become minus. This is negative, become positive. Then what can we do? The same idea. We need to reciprocate all the functions. So for me to move this one to the Vn and this one to the x, I need to reciprocate it. So I'm going to have Vn plus 1 divided by, so there is minus there. Or I can even leave the minus here. So I'll just have Vn squared minus Vn plus 1, the Vn. Then I left the minus here. I didn't send the minus. So here still the minus will be there, the x. So that's what I'm going to get. Now we learned that, look at this. We learned that, what is it? We learned that this Vn squared minus 2 Vn plus 1 was equal to this. But the question is, can we do same thing to this one too? Can we do that? No, unless this one is squared before we can do that. So now the question is, how can we integrate this? So that's basically the question, the big question that we need to ask ourselves right now. So we want to integrate Vn plus 1 divided by Vn squared minus Vn plus 1 the Vn, which is equal to minus integration of 1 over x dx. I'll relax and do that. But what we can do here is, now we need to split some of the functions so that we can do it very well, because basically the idea is that how you'll be able to split the function in such a way that you can work it out. So let's see how we can split this function here and see what we are going to get. So this function here can be written as, let's say, 2 Vn, let me say, minus 1 plus, and then this one is going to be Vn, yeah, Vn plus 2. Is that right? Yeah, so 2 Vn, okay, so this one should be minus. Okay, I can just maintain this one and make this one minus and make this one to minus. So I just want to integrate. So I want to use a master scale to do that. I want to separate this one because of the way this one is. Why am I doing this? I'm doing this because, look at this. When I differentiate this with respect to Vn, I'm going to have 2 Vn minus 1. So I'm doing that so that I can do some substitution here, so that I can work with that one, that aspect there. So basically that's what I'm trying to do from there. So now this is the same as this, because 2 Vn minus Vn is Vn, and then minus 1 minus minus will be plus. I'll have something like this. This divided by Vn squared minus Vn plus 1 the Vn. And we know that this is basically going to give us the natural log of x plus c1. So the only problem here is now this guy. So that's what we just need to work through. So I can split the integration to 2 Vn minus 1 divided by Vn squared minus Vn plus 1 the Vn, minus now Vn minus 2 divided by Vn squared minus Vn plus 1 the Vn, which is equal to minus this plus c1. So integration, it's kind of, you need to find your own way of doing that. So this one, as I said, if I let u to be equal to Vn squared minus Vn plus 1, then the Vn over the du over the Vn will be 2 Vn minus 1, right? So du will be equal to, oops, yeah, I think, is that right? Yeah, du will be equal to 2 minus 1 divn. Good. So when I do back substitution, we see that now the integration, and let's see how we can also go with this guy here. This guy here. Okay, I'll come back and come and do this one. So let's focus on this one and see what we are going to get. This is the last question. So when we are done, I'll just give you a trial one. So now it means that this one, the one that with red, it now is going to be 2 vn minus 1 divided by vn squared minus vn plus 1 divn. This is going to be integration. Now you see that du is the same as 2 vn minus 1 divn. So 2 vn, or I can write this one as now divn is the same as du divided by 2 vn minus 1. So this is going to be 2 vn minus 1 divided by u, because everything here is u, and times du divided by 2 vn minus 1, and this guy will cancel this guy. So I'm going to have integration 1 over u divn, and this is the same as natural log of u. We are not done with the integration, so I'm not adding constant because we have this one to it. So this is going to give us, now we know that u is equal to this, so this is going to give us the natural log of vn squared minus vn plus 1. So this side, that's what you are getting now. Good, that's what we are getting for that side. Then let me add another page so that we can use it. So now that you've gotten this side, let me write everything here. So now we know that we've gotten natural log of vn squared minus vn plus 1. Is that right? Yes. So this side is giving us the natural log of this, right? So now we need to focus on this one. So minus, so we need to focus on this guy, but I can split this guy into 2. So I'm going to have minus, okay, let me write it before I split it. So vn minus 2 divided by vn squared minus vn plus 1 divn is equal to minus natural log of x plus c1. Is that right? Good. So that's what we have now. Now let's split them into 2. I'm going to have this one to be natural log of, so let me just pick this guy and just solve it and bring it back. So let's pick vn minus 2 divided by vn squared minus vn plus 1 divn. So the idea is that you should be able to you should be very good with integration, how to look at the function and see how you are going to work with that. This can be written as vn divided by vn squared plus minus vn plus 1 divn minus 2 divided by 2. Let me see something here. If I let this one to be this, can I do something about this? No. Okay, I can't do anything about this. If I factor here, if I do something like minus 1 minus 1, good, good. I saw a new way of doing this so that this one becomes very nice to go with it. Instead of splitting it into 2, I can write this one as integration vn minus 1 minus 1. Good. Vn squared minus vn plus 1 divn. So you see, we need to find a strategy of doing this. Minus 1 divided by vn squared minus vn squared minus vn plus 1 divn minus, good, 1 over vn squared minus vn plus 1 divn. Good. So we're able to do this. Now this one too, we are going to use substitution again. Yes, we are going to use substitution again, but let me see when we differentiated. Okay. No, this is not going to work. This is not good. When you differentiate it, this is not good. For me to get it that way, I need to make this one half. Doing it half. So if this one is half, okay, let me make this one half. Then this one should be, is this one going to give us 2? Yes, of course, this is going to give us 2. Good. So let's do it this way. Let's do it this way. I do it this way, and I'm going to have this, and this one will be good. So that now here, if I let u to be equal to v squared minus v plus 1, the u over the v will be equal to what are we going to get? 2v minus 1. Good. Then when I factor When I factor 2 out, I'm going to have v minus 1 over 2, which is right here. And then this is with the v. So I'm going to have, now the integration is going to be integration. Now v minus half, and the v is this. Which, okay, so this will imply that du over 2 is equal to v minus half times the v. So this would, together with this one, is equal to du over what? 2. So I'm going to have 1 divided by u times du over 2. This is a skill set. So 1 over 2, 1 over u du, and then this is going to give us 1 over 2 natural log of v. So still we are not done with the integration. So this is going to give us 1 over 2. Then is u is v squared minus v plus 1. Wow. Wow. So now what is left is this guy. Hey God, how can we do this one too? Okay, let's try and see if we can find a way around it. So let me shift this guy here. So we've done this one. So let's focus on this guy. Now, focusing on this guy, what we can do here is we need to definitely try and then simplify the denominator. That's all that we need to do. If not, we cannot do that. So I'm thinking of seeing something like, since this one is squared, seeing something like, let's say, tan inverse or something like that. So the denominator, so I can write the denominator v squared minus v plus 1 as v minus 1 over 2 squared plus 3 on 2. Is that right? Because when I multiply this, we have v squared minus v plus 1 over 2 plus 3 on 2. And this is going to give us, okay, let me make this one 4. If I make this one 4, then this is going to give us, okay, this one will be 4. Okay, then this one is going to give us 1. Good. So this is true. So let us express the denominator here as this. So we are going to have, so from here, this one I can factor it out. So I'm going to have something like this, minus 3 on 2, 1 divided by, so the denominator is now v minus 1 over 2 squared plus 3 on 4, the v. So I'm using the idea of thinking of getting something called tan inverse, right? Something like that. So what I'm going to do is I'm going to let u to be equal to v minus 1 over 2. Right, good. So now this implies that the v over the u over the v is 1. So this implies that the u is the same as the v. And what are we going to get? This is now minus 3 on 2 integration 1 divided by, the whole of this is u. So I'm going to have u squared plus 3 on 4 du, because the vein is the same as du. Now we need to think about tan, right? Because tan is something like something squared plus 1. So we need to think about tan inverse. So this is what I'm going to do. We need to be very smart here, right? Because we know that if I integrate 1 divided by vein squared plus, let's say, if this one is 1 dx, or let's say the vein, this is going to give us tan inverse of vein. But if this one is not 1 and we have something like vein squared plus a squared, which is equal to, this is the same as 1 divided by a tan inverse of vein over a. So something like this. That's what we need to have in mind. So we have something like this. So it means that we need to manipulate it so that it suits this. Because since this one is not 1, if this one is 1, then this one just going to be tan inverse of u. But since this one is not 1, it's like kind of, this one is a. But this a here is squared, so we need to make sure that we square it. So what are you going to do? We can write this one as minus 3 on 2, 1 divided by u squared plus, now how can I write this one as a squared? I can write this one as square root of 3 over 4 all squared. Doing this, because I know that square root of this all squared, this one will cancel this, and I have this one already. So that now I can compare this to this. So I can see that vein is u and a is that. So this is going to help us to write this one as minus 3 on 2 arctan or tan inverse. Oops, this one should be times. So this times 1 over a. A is root of that. So a is 1 divided by root of 3 on 4 tan inverse of vein is u, so u divided by root of 3 over 4. This is magic. I can't believe this. Now, let me just finish this up. Open a page. So we have this guy. Let me write it down. So ln of vein squared minus vein plus 1, and then minus the whole of everything that we are going to write. So minus this, but this one we had it to be that. So we have minus here. So don't forget, we are going to have minus 1 over 2 ln of vein squared minus vein plus 1. Then we are doing another minus this. So this is minus coming out, and we are going to have it positive. So we are going to have plus 3 on 2, but we can write root of 3 over 4 as root of 3 divided by root of 4, which is the same as root of 3 divided by 2. So we can write this one as that. So I'm going to have times 1 divided by root 3 over 2, then the arctan or tan inverse of 1 divided by u divided by root 3 over 2. Then this is equal to, so don't forget, this is supposed to be equal to minus ln of x plus c1. I think I'm done with the integration, so I need to add plus c to it. So plus c2 here. So that is what we have here. So now what can we do? Let's try and simplify something. I can add this to this, and I'm going to have half ln of vein squared minus vein plus 1 plus, now this is the same as this is 3 over 2 times 2 over root of 3. So 2 cancel 2. So I'm going to have 3 over root of 3. Then the tan inverse of this is going to give us, it will reciprocate it. So this is going to give us 2u divided by root of 3 plus, or is equal to minus natural log of x plus C1 minus C2. Now we know U, right? What was U? U is equal to this, Vn minus half. So let's plug it in. 1 divided by Vn squared minus Vn plus 1 plus this one can be written as, I think this is the same as that, because 3 divided by this multiplied by this multiplied by this. This is 3 root 3 divided by 3. Okay, cancel out. So we are getting the same thing as this. So this is tan inverse of, now we said U is the same as Vn minus half. So this is 2 Vn minus half divided by root 3. Good. This is minus ln x plus c. Now we know Vn, right? Let's go and bring Vn. From our first substitution, we said Vn should be the same as y over x. So let's just go and plug them in. So I'm going to now have 1 divided by 2 ln of y divided by, let me use square bracket here, squared minus y over x plus 1 plus root of 3 tan inverse of 2 Vn is y over x minus 1 over 2 divided by root of 3 is equal to minus ln of x plus c. So this is the general solution. We don't need to simplify because this is kind of complicated. So before I show you the trial question, I just need to go back and then just explain everything back again to you. Like a kind of, I think this one is crazy with the integration. So we all know how to go through this, right? We learn how to do this and then how to set up all this. I think this kind of very simple. But let me talk about the integration again. So when we had this integration here, we need to develop a strategy of doing them. So the first thing that I saw was, I saw that when I differentiate this, I'm going to have 2 Vn minus Vn. So I need to manipulate it in such a way that I get something like that on the top, so that it can help me in that aspect. So what did I do? I break this one into this, right? I break this one into that. So that's what I did. But another way that I can also do this, you can just break them in different forms. It's basically how it can help you to do the integration. That's what that's what matters a lot. So basically you can break them into any way, the way you want it to be. So from here, I could have even used this one and break it to the other stuff. It is going to also help the same thing. So I break this one into this, or even you can break Vn plus 1 to something like, let's say, Vn minus half and then plus 3 over this. I think this one could have even helped very faster. So I could have break this one into this and just used to solve. But I didn't do it that way. Yeah, this one could have been nice if I break that one that way. Yeah, but better still, it's okay. So we're able to break this one, and then I took this part with the denominator, which is this, and then I took this part with the denominator, which is also this, and then I just solved this part using substitution, and then we had this one here. So now this is equal to this, so I added it to this here. Then now I break, I took this guy and then I break this guy into this form. So as I said, if you want to try it again, you can simplify it. You can break the top to this so that it becomes very simple, so that you can pick this with the denominator, right? This one's supposed to be Vn. You can pick the first one with the denominator here, one side, solve it, and then pick this one with this one. So you see that this one with this one was the last term that we solved here. This one, good. It's like this term here. Yeah. And then the one here, this one here is kind of like the other term that we solved here. Is that right? It's half. Let me check something here. This is the same as, no. Okay, minus half minus 3 on 2. This is the same as minus 4 divided by 2, which is minus 2. Okay, that's right. That's right. That's right. I thought I had it wrong. Yeah. So basically, that is how, just go through the video again and just do it. But if you want to go it in other way, you can think of this and then you just write it out, and you are going to get the same results, the same thing, the same results that you are going to get at the end of the video. Yeah. So this is the general solution. So try this and then just leave your final results in the comment section. So check if it is homogeneous, and then when you finish, try and find the general solution using the homogeneous differential equation. So in the next video, guess what we are going to talk about? In the next video, we are going to discuss another method, which we call it exact differential equation. Now, the idea is that if the function is not separable and it is not homogeneous, then it is not exact. So we need to find integrating factor to multiply through, and then it's going to help us to basically solve again and get back to where we want to go again. So now let's go to the next video and then talk about exact differential equation. See you in the next video. I hope you've gotten the question. Yeah.